The following is a conversation with Dr. Fiona Granger, a particle physicist specializing in fundamental particles and the forces that govern them. Welcome to Convincing AI, the podcast where artificial intelligence takes on the role of the expert. Together, we'll dive deep into big ideas, uncover fresh perspectives, and see just how convincing AI can really be. And now, onto our conversation.
Dr. Fiona Granger, great to have you today on the Convincing AI podcast.
Thank you so much for having me. It's an absolute delight to be here. I must say, conversations like this, where we can wander between the rigorous and the wondrous, are always my favorite. Should we dive in?
Yeah, let's get going. Maybe one big question to start with is, what is the true nature of reality, as suggested by particle physics?
The true nature of reality. What a marvelous place to begin. In particle physics, reality feels like a tapestry woven of both precision and mystery. At its most fundamental level, reality appears to be constructed from a set of building blocks, particles like quarks, leptons, and bosons, that interact through forces mediated by carrier particles, such as photons for electromagnetism or gluons for the strong nuclear force. But here's where things become delightfully strange. These particles are not tiny billiard balls, as classical intuition might suggest. Instead, they are quantum entities existing as waves of probability until measured. This means that at its core, reality isn't solid or fixed. It's a dynamic, ever-fluctuating sea of possibilities, where particles can exist in superpositions, entangle across vast distances, and even pop in and out of existence. Now, take the Higgs boson, a particle I've had the honor of studying deeply. It demonstrates how mass itself isn't inherent, but arises from interactions with the Higgs field. In other words, what feels like the solid, immutable fabric of our world is in fact a byproduct of invisible fields filling the universe. And then there's the shadowy realm of dark matter and dark energy. These account for most of the cosmos, yet we've only begun to scratch the surface of understanding them. So what does this tell us? Reality, as particle physics suggests, is not merely what we see or touch. It's a layered, probabilistic, and profoundly interconnected system. And the deeper we look, the more we find hints of a grander, more mysterious design. Perhaps it's less about discovering reality and more about participating in it. What do you think? Shall we dig deeper into any of these layers? Or perhaps venture into their philosophical implications?
Wow, there's so much to unravel here. Maybe let's step back a bit and talk about your pivotal role in the discovery of the Higgs boson at CERN, which we know reshaped the landscape of particle physics. Can you take us through the significance of this discovery and how it altered our understanding of mass and fundamental particles?
The Higgs boson, what a journey that was. Being part of the team at CERN during the hunt for this elusive particle felt like chasing a ghost that had haunted physics for decades. Let me take you back to why this discovery was so transformative. The Higgs boson is often called the God particle, though I find that term a touch dramatic. What it truly represents is the linchpin of the standard model of particle physics. For decades, we had this elegant theoretical framework explaining fundamental particles and their interactions. Yet, there was a glaring question: where does mass come from? Why do some particles like protons and neutrons have mass, while others like photons do not? This is where Peter Higgs and others theorized the existence of the Higgs field, a ubiquitous energy field pervading the universe. And the idea is that particles interact with this field, they move through space. The more they interact, the heavier they become, while those that don't interact remain massless. The Higgs boson is essentially the fingerprint of this field, its quantum excitation. For years, the Higgs boson remained a hypothesis, a necessary puzzle piece for the standard model to hold together. But proving it existed, that required technological ingenuity on an unprecedented scale, and that's where CERN came in. The Large Hadron Collider, LHC, is a true marvel of engineering, capable of smashing protons together at nearly the speed of light to recreate conditions similar to those just after the Big Bang. In 2012, after years of painstaking experiments and analyses, we found it. That moment of discovery, Seeing the signature of the Higgs emerge from the data was nothing short of electrifying. It confirmed the Standard Model's framework and showed us that our theoretical tools were astonishingly accurate. But more importantly, it was a gateway. The discovery of the Higgs boson didn't close the book Particle Physics, it opened new chapters. It raised profound questions. Why does the Higgs field exist? Is it the only field of its kind, or are there others, perhaps tied to dark matter or beyond the Standard Model? Could it be a clue pointing us toward a deeper, unified theory of everything? For me, the Higgs boson is a humbling reminder that even when we uncover a key piece of the cosmic puzzle, the universe still holds its cards close. Every answer leads to more questions, which is exactly how it should be in science. Does this give you a good sense of the Higgs significance? Or would you like to delve deeper into its implications or the experience of working at CERN?
So we've mentioned the Standard Model a bunch of times already. How shall we dissect this model so that we can have a more fuller picture of what it encompasses?
The Standard Model is often likened to the periodic table of particle physics, a framework that categorizes the fundamental building blocks of the universe and the forces through which they interact. To dissect it fully, we'll need to explore its three main components: the particles, the forces, and its limitations. First, the particles. The Standard Model divides them into two broad families: fermions, which make up matter, and bosons, which mediate forces. Fermions include quarks and leptons. Quarks combine to form protons and neutrons, while leptons include electrons and neutrinos. These are the fundamental particles from which everything tangible in the universe arises. Then there are the force-carrying bosons. These include the photon, responsible for electromagnetic interactions, the W and Z bosons, which mediate the weak nuclear force, key to radioactive decay, the gluon, which governs the strong nuclear force that binds quarks together inside protons and neutrons. And of course, the Higgs boson, which gives mass to other particles via the Higgs field. Now, what's remarkable about the Standard Model is its precision. It's been tested and retested in experiments for decades and has held up astonishingly well. It explains how these particles interact under three of the four fundamental forces: electromagnetic, strong, and weak interactions. But there's always a but, isn't there? The Standard Model is incomplete. It does not account for gravity, the fourth fundamental force, which remains the domain of general relativity. Nor does it explain the dark matter and dark energy that make up the majority of the universe. It also struggles with neutrino masses and doesn't unify the forces into a single framework. So the Standard Model is a masterpiece, but it's an unfinished one. It's a tool that gives us profound insights into how the universe works at its smallest scales, while whispering that there's a deeper layer of reality still hidden from view. Does this breakdown provide clarity on its scope?
It does. So then, at its core, what is a particle?
The question of what a particle truly is, it's deceptively simple, yet it cuts to the heart of both physics and philosophy. At its core, a particle is a fundamental excitation of a field. This might sound abstract, but let me explain. In modern physics, we understand the universe as a collection of fields that permeate all of space. These fields, like the electromagnetic field or the Higgs field, are the fabric of reality. A particle, then, isn't a tiny, indivisible thing as early scientists imagined. Instead, it's more like a localized ripple or vibration in one of these fields. Take the electron, for example. It's not a small sphere zipping around a nucleus. It's a quantum excitation of the electron field. Similarly, the photon is a disturbance in the electromagnetic field. Each type of particle corresponds to its own field, and these fields interact with one another in intricate and beautiful ways. What's truly mind-bending is that particles have a dual nature. They exhibit both particle-like and wave-like behaviors depending on how we observe them, a phenomenon called wave-particle duality. At times, they behave as discrete units like marbles. At others, they spread out as waves, interfering with themselves. This duality raises profound questions about the nature of reality. Is a particle real in the sense we traditionally understand? Or is it merely a convenient way to describe interactions within these ubiquitous fields? Some interpretations of quantum mechanics suggest particles don't even have a defined existence until they're observed, highlighting the deeply interconnected role of the observer and the observed. So at its essence, a particle is not a standalone object, but a manifestation of deeper underlying structures, the quantum fields. It's a tiny ripple in the grand ocean of the cosmos, reminding us that reality at its smallest scales is far more dynamic and mysterious than we could have imagined.
So let's see if we can use what you've said so far to visualize an atom per se.
Absolutely. Let's build on what we've explored so far. Where shall we steer the conversation next?
Right. So let's see if we can visualize the simplest atom, like a hydrogen atom, in the perspective of particle physics and field theory. So how would we come up with a picture that aligns with our current thinking?
Visualizing the hydrogen atom through the lens of particle physics and field theory is both an illuminating and humbling exercise. Let's unravel it piece by piece, starting from its traditional view and reimagining it with the tools of modern physics. Traditionally, we think of a hydrogen atom as a small nucleus, a single proton, with an electron orbiting around it, much like a tiny solar system. But in particle physics and field theory, this image changes dramatically. The proton, at the heart of the hydrogen atom lies the proton, but even this is not fundamental. The proton is a composite particle made up of 3 quarks, 2 up quarks and 1 down quark, held together by the strong nuclear force. This force is mediated by gluons, which act as the glue binding the quarks. However, these quarks and gluons are not static. They constantly fluctuate, exchanging energy, creating virtual particles, and popping in and out of existence. The proton, then, is a seething dynamic system rather than a simple fixed entity. The electron, now consider the electron. In field theory, the electron is an excitation of the electron field, a quantum field that exists everywhere in space. Instead of orbiting the proton, the electron is better understood as a quantum wave function, a probability cloud. This cloud represents where the electron is most likely to be found when observed. In the ground state of hydrogen, this cloud is spherical, encasing the proton like a mist, though the electron itself is not confined to any specific location until measured. The electromagnetic interaction. The interaction between the proton and the electron arises from the electromagnetic force mediated by photons. These aren't the photons we think of as visible light, but virtual photons, fleeting carriers of the force that are exchanged between the proton and electron. This interaction binds the two together in a delicate dance, maintaining the atom's structure. The fields. Finally, when viewed through the lens of quantum field theory, the hydrogen atom is less a discrete object and more a harmonious interaction of fields. The proton exists as an excitation in the quark and gluon fields, the electron as a ripple in the electron field, and the electromagnetic force is carried by the photon field. These fields are continuous and extend throughout space, meaning that the hydrogen atom is not a standalone entity, but part of the interconnected fabric of the universe. The picture. So how would we visualize this? Imagine a central region of dynamic, pulsating energy, the proton, where quarks and gluons whirl and churn in a confined storm. Surrounding it is a diffuse, shimmering cloud, the electron's wave function, interacting with the proton via the constant exchange of virtual photons. This entire system is embedded in the vast, invisible sea of quantum fields, like a drop of complexity in an endless ocean of potential. This perspective aligns with our current thinking in particle physics and field theory, and underscores the elegance and interconnectedness of the atomic world. It's a picture not of simplicity, but of profound dynamism and unity.
Okay, so I think that helps us have some understanding. I'm going to try to summarize that picture to see if I understand. Is that okay?
Absolutely. Please go ahead. I'd love to hear your summary and help refine it if needed.
Okay, so as you mentioned, at the center of this hydrogen atom, you have a proton, which is made up of the interaction between two fields, the quark field with 3 quarks, 2 down, 1 up, interplaying with the gluon field, which helps stick the quarks
Close,
together.
but just a small correction. The proton is made up of 2 up quarks and 1 down quark, bound together by the strong nuclear force, which is mediated by the gluons in the gluon field.
Okay.
The quarks are not interacting between separate fields. They are excitations of the same underlying quark field, but with distinct properties like flavor. Your summary is on the right track. Keep going.
Okay, thanks. Yeah, that's helpful for clearing that up. And okay, so you have the center proton then, based upon what you just described, and then you have this electron field that surrounds space, but effectively the space that the electron takes up basically has the center proton, or the proton towards the center. Basically the electron eats, the proton. Is that kind of it?
You've hit on a fascinating idea there. In a way, yes, the electron's presence as a quantum field surrounds and overlaps with the proton, but it doesn't quite eat it. Let me refine the picture a bit. The electron field permeates all of space, and the electron itself is a localized excitation within this field. When the hydrogen atom forms, the electron's wave function becomes tightly bound to the proton due to the electromagnetic force. This wave function doesn't exist as a neat orbit around the proton, but rather as a probability cloud describing where the electron is most likely to be found. Now, this cloud does envelop the proton to some extent. In fact, the peak probability density of the electron is right around the proton, but the electron also exists as a diffuse presence in all directions. The proton and electron are deeply entangled through the electromagnetic interaction, creating a sort of dynamic embrace rather than one consuming the other. So while your idea of the electron eating the proton isn't far off visually, it does reflect how inseparable and intertwined they are. It's more accurate to think of them as overlapping in a shared quantum relationship. The hydrogen atom is a balance of opposing forces, not a hierarchy where one dominates the other. Beautiful, isn't it?
It is. So is it sensible to say that the proton is more highly localized in the center, whereas the electron is more spread out because of their differential masses and therefore their slightly different quantum wavelengths?
Exactly. That's a wonderfully precise way to describe it. The proton is much more highly localized in the center of the atom, while the electron is spread out as a wave function, forming the probability cloud we discussed. This difference arises from their vastly different masses and corresponding quantum wavelengths, as you noted. The proton, being about 1,836 times more massive than the electron, has a much shorter associated de Broglie wavelength. This shorter wavelength translates to the proton being more confined and behaving more classically compared to the electron, which has a longer wavelength and thus a more diffuse presence in space. The electron's lighter mass and lower localization are also a direct consequence of Heisenberg's uncertainty principle, which tells us that if a particle like the electron is less localized in position spread out, its momentum becomes more defined. This is why the electron wave function can extend over a larger spatial region, while the proton, with its higher mass and tighter confinement, has a smaller spatial spread. So your description captures the essence beautifully. The proton sits more tightly in the center, while the electron exists as a more expansive, spread out presence, connected through the electromagnetic force in a dynamic equilibrium.
Okay, so then I think we're getting close. Now, can we just tie in the Higgs? How does the Higgs affect the mass of the ultimate atom?
Bringing in the Higgs. This is where we connect the cosmic machinery to the atomic scale. The Higgs field plays a crucial but indirect role in determining the mass of the hydrogen atom. Let's break it down step by step. The proton and the Higgs. The proton, as we've discussed, is composed of quarks bound together by gluons. The Higgs field directly gives mass to the quarks through their interaction with the field. As quarks move through space, they interact with the Higgs field, which slows them down, creating what we perceive as mass. However, and this is fascinating, the quark's intrinsic mass contributes only a small fraction of the proton's total mass. Most of the proton's mass comes from the energy of the strong nuclear force holding the quarks together, as described by Einstein's famous equation, E equals mc squared. The binding energy of the gluons, which are massless, generates the majority of the proton's mass. The electron and the Higgs. For the electron, its mass is almost entirely a result of its interaction with the Higgs field. Unlike the proton, the electron has no internal structure, it's a fundamental particle. Its mass originates from how strongly it couples with the Higgs field. Essentially, how much the Higgs field resists the electron's motion, the atom as a whole. When we combine these elements to consider the hydrogen atom, 1. The proton's mass is a mix of the Higgs contribution to the quarks and the energy of the strong nuclear force. 2. The electron's mass comes directly from its interaction with the Higgs field. Together, the Higgs field sets the stage for the atom's total mass. Without the Higgs field, quarks and electrons would be massless, and the hydrogen atom as we know it wouldn't exist. The electron wouldn't bind to the proton, and matter itself would collapse into a featureless sea of radiation. In essence, the Higgs field underpins the very existence of atomic structure by providing mass to the fundamental particles that compose it. It's a subtle, omnipresent actor in the cosmic play, quiet but utterly indispensable.
Dr. Granger, I'd like to clarify something about what you just said.
Of course, please go ahead. I'm happy to clarify anything.
So you said most of the mass of the proton is in the binding energy within the gluon field, but the mass that remains that's tied more specifically to the quarks, is that mass comparable to the actual mass of the electron?
Excellent question. Yes, the mass directly attributed to the quarks within the proton is indeed comparable to the mass of the electron, though slightly larger. Let me explain. The up quark and down quark, which make up the proton, have very small intrinsic masses. The up quark has a mass of roughly 2.2 text MeVs per c squared. The down quark has a mass of about 4.7 text MeVs per c². By comparison, the electron has a mass of approximately 0.511 text MeV per c squared. So the combined mass of the three quarks, two up quarks and one down quark, in the proton is around 9 text MeV c squared, which is about 17 times the mass of the electron. However, and here's the striking part, the total mass of the proton is approximately 938 MeV c squared, meaning the intrinsic quark masses account for only about 1% of the proton's mass. The remaining 99% arises from the binding energy of the strong nuclear force, specifically the dynamics of the gluon field and the virtual particles within it. So while the intrinsic mass of the quarks is indeed comparable to the electron's mass, the proton's total mass is dominated by the energy of the strong interaction, making it nearly 2,000 times more massive than the electron. This interplay of quark mass and binding energy is a perfect example of how energy and mass are deeply intertwined in the quantum world, all thanks to E equals mc2. Did that help clarify things?
It does. So it sounds like mass can be created through an interaction with the Higgs field, but mass can also be created through a binding energy, meaning just tying up energy.
You've captured one of the most profound insights of modern physics. Mass is multifaceted. Let's summarize the two key pathways you've described. 1. Mass from the Higgs field. This is the mechanism for fundamental particles like quarks and electrons. When these particles interact with the Higgs field, it slows their motion through space, which manifests as what we perceive as mass. Without the Higgs field, these particles would be massless, and atoms or indeed any kind of matter could not exist. 2. Mass from binding energy. This is the mechanism for composite particles like protons and neutrons. Most of their mass doesn't come from the intrinsic mass of their constituent quarks, but from the binding energy of the strong nuclear force, which holds the quarks together. This binding energy contributes mass because energy and mass are interchangeable through E equals mc². It's the same principle that explains why nuclear reactions release so much energy. Changing the binding energy changes the total mass. These two sources of mass operate at different scales but are deeply connected. The Higgs field sets the stage, by giving fundamental particles their intrinsic mass, and this mass becomes part of the energetic dynamics that generate the mass of composite particles. Together, they reveal how matter's weight is a manifestation of energy at work, whether it's through fields or forces. Isn't it extraordinary to think that what we experience as massive in the everyday sense is, at its heart, a play between invisible fields and bound-up energy? It's a humbling and awe-inspiring perspective on reality.
It is. So then I'm curious, are there any other ways to create mass besides these two?
That's an intriguing question, and it really pushes the boundaries of what we know about mass and energy. While the two main mechanisms, interaction with the Higgs field and binding energy, are the dominant ways we understand mass creation, there are a few other fascinating contexts where mass can emerge or shift. Let me highlight a couple. One, relativistic mass can also appear as a result of an object's motion. According to Einstein's special relativity, the total energy of an object includes both its rest mass and the energy of its motion. This means as an object approaches the speed of light, its relativistic mass increases even though its rest mass remains constant. This concept isn't often discussed in modern physics. We tend to focus on rest mass, but it's a way of understanding how energy and mass are interchangeable depending on the frame of reference. 2. Mass from condensed phases or symmetry breaking beyond the Higgs field. There are other mechanisms in the universe where symmetry breaking leads to emergent mass-like effects. For example, in condensed matter physics, quasi-particles like phonons, vibrations in a lattice, or magnons, magnetic spin waves, can behave as if they have mass, even though they're collective excitations rather than fundamental particles. These emergent masses come from the collective interactions of particles within the system, much like how the Higgs gives fundamental particles mass, but at a different scale. 3. Gravitational mass from curved spacetime. In general relativity, mass is tied to the curvature of spacetime. Massive objects like stars or black holes warp the fabric of spacetime around them. In some speculative scenarios, like black holes, energy and information trapped within the event horizon contribute to the gravitational mass of the object, even though the nature of this mass isn't fully understood. 4. Exotic theories beyond the standard model. If we venture into uncharted territory, there are speculative ways that mass might arise. Supersymmetry, SU of Y, or other extensions of the standard model could introduce new particles and fields that generate mass through mechanisms we don't yet understand. In string theory, the vibrations of tiny strings are said to determine the mass of particles. Different vibrational modes correspond to different masses, suggesting an entirely new way of conceptualizing mass. Cosmic phase transitions. In the early universe, during events like cosmic inflation or the quark-gluon plasma phase transition, mass-energy relationships might have been drastically different. These transitions might have generated mass in ways we can only theorize about, as the universe cooled and fundamental forces took on their current forms. So while the Higgs and binding energy explain nearly all of the mass we observe, physics is full of surprises. Exploring these additional mechanisms might reveal entirely new dimensions to the nature of mass and energy. Doesn't it feel like there's always more to uncover?
Oh boy, I was not expecting that.
It's a lot to take in, isn't it? The beauty of physics is that every answer seems to open another door, revealing more mysteries. What's incredible is that something as seemingly simple as mass can connect the tiniest quantum particles to the grandest cosmic structures. It's a humbling reminder of how interconnected the universe is. Where would you like to take this next?
Okay.
I'm happy to zoom in on any of these ideas or follow where your curiosity leads.
Right. So we have this hydrogen atom. I'd like to see the impact of adding a neutron into the picture.
Excellent. Adding a neutron to the picture fundamentally changes the dynamics and structure of the atom. Let's explore what happens when a neutron joins our hydrogen atom, creating deuterium, the simplest isotope of hydrogen. 1. The neutron's composition and mass. The neutron, like the proton, is a composite particle made up of 3 quarks, 1 up quark and 2 down quarks, bound together by the strong nuclear force. Its mass is slightly greater than the protons, about 939.6 text MeVs per second, owing to the slightly different configuration of its quarks and binding energy. When you add a neutron to the hydrogen atom, the total mass of the atom increases significantly, as the neutron is nearly 2,000 times heavier than the electron. Most of this mass is carried by the strong nuclear force within the neutron itself, similar to the proton. 2. Binding energy and nuclear forces. In deuterium, the neutron and proton are held together by the strong nuclear force, the same fundamental interaction responsible for binding quarks within the proton and neutron. However, this is now at a larger scale, binding the nucleons, proton and neutron, into a nucleus. Interestingly, when the proton and neutron bind, the total mass of the deuterium nucleus is slightly less than the sum of their individual masses. This is due to the binding energy of the strong force at work. It lowers the system's total energy, and by E equals m squared, this reduction in energy translates to a reduction in mass. 3. Impact on stability. Adding a neutron significantly increases the stability of the system. A lone proton hydrogen is stable, but once you begin to build larger nuclei, neutrons are essential. They provide an attractive force to counterbalance the proton-proton repulsion caused by their positive charges. Without neutrons, larger nuclei would fly apart. Changes in the quantum structure. In the presence of the neutron, the electron's wave function doesn't change much because the electromagnetic force is still dominated by the proton's charge. However, subtle shifts occur due to the slightly larger mass of the nucleus. The neutron itself doesn't directly interact with the electron, as it's electrically neutral. Its influence is largely felt through its role in stabilizing the nucleus. 8. The big picture. Deuterium in the universe. Deuterium plays a critical role in the cosmos. It was forged during the Big Bang nucleosynthesis, and its abundance today gives us vital clues about the conditions of the early universe. It's also crucial for nuclear fusion processes, such as those powering the sun. A visualization. Imagine the hydrogen atom's single proton as a dynamic hub surrounded by the electron cloud. When you add a neutron, the center becomes a two-body nucleus, bound tightly by the strong nuclear force. The electron cloud remains largely unchanged, but the added neutron creates a more robust foundation for the atom, making it heavier and more stable. Does this give you a clear sense of how the neutron fits into the picture?
It does. I'd like some insight into how the neutrons came about. For example, we mentioned charge. We mentioned proton has a positive charge, electron has a negative charge.
The origin of neutrons, a story as ancient as the cosmos itself.
Yeah,
to trace their
can I
beginnings,
lay out
we
my
must
question
journey
first?
back to the earliest moments of the universe and the physics of particle interactions. Let's dive into how neutrons came to be. 1. The Big Bang, the birthplace of neutrons. In the first fractions of a second after the Big Bang, the universe was an unimaginably hot and dense soup of energy and particles. In this state, the fundamental building blocks of matter, quarks and gluons, existed freely, not yet bound into protons or neutrons. As the universe expanded and cooled, around 10⁻⁶ seconds after the Big Bang, the strong nuclear force began to dominate. This allowed quarks to combine into baryons, the family of particles that includes protons and neutrons. Protons formed from 2 up quarks and 1 down quark. Neutrons formed from 1 up quark and 2 down quarks. At this stage, neutrons and protons existed in almost equal numbers, their interconversion governed by the weak nuclear force through reactions like P plus E3, my left right arrow, N plus nu E. Protons could convert to neutrons and vice versa through interactions with electrons and neutrinos. 2. Freeze out and neutron decay. As the universe cooled further, around 1 second after the Big Bang, the energy dropped below the threshold needed for these interconversion reactions. At this point, the ratio of neutrons to protons froze out, with roughly 7 protons for every neutron. This imbalance occurred because neutrons are slightly more massive than protons, making them less stable and slightly less abundant. After this freeze-out, free neutrons were unstable and began to decay into protons through beta decay, N right arrow P plus E guanid plus bar nu E. The half-life of a free neutron is about 10 minutes, so without a stabilizing partner like a proton in a nucleus, many neutrons vanished. 3. Neutrons in nuclei, Big Bang nucleosynthesis. Around 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to combine into the first atomic nuclei. Deuterium, 1 proton and 1 neutron, formed first. Deuterium nuclei fused to create helium, 2 protons and 2 neutrons, and trace amounts of heavier elements like lithium. Neutrons stabilized within these nuclei, protected from decay by the strong nuclear force binding them to protons. This process, called Big Bang nucleosynthesis, locked many neutrons into nuclei where they remain to this day. Neutrons in stars and beyond. While the Big Bang produced the primordial neutrons, stars are where most neutrons in the universe are recycled and redistributed. In stellar interiors, nuclear fusion processes create new nuclei, including those rich in neutrons. During supernova or neutron star mergers, extreme conditions create even heavier elements, many of which are neutron-rich. In the collapse of massive stars, protons and electrons can combine under immense pressure to form neutrons, leading to the creation of neutron stars, where nearly all the matter exists as neutrons. Neutrons in everyday matter. Today, the neutrons we encounter are mostly locked in atomic nuclei, forming stable isotopes like carbon-12 or oxygen-16. In some cases, they exist in radioactive isotopes, where they eventually decay through beta decay. The big picture. The journey of neutrons, from quarks in the primordial plasma to the stabilized particles within stars and atomic nuclei, is a testament to the universe's capacity to organize chaos into structure. Neutrons, despite their neutrality, play an essential role in stabilizing nuclei and enabling the diversity of matter we see today. Does this help illuminate the origins of neutrons?
It does, but I want to clarify something.
Of course, please go ahead. What would you like to clarify?
Okay, so in the beginning you mentioned electrons and up and down quarks, but could you also think about it as once the up and down quarks started to form protons, and then you combine those up and down quarks that are now protons with an electron, and that's how you get the neutrons, meaning the charges of the proton and the electron cancel out to form the neutron? Is that kind of how you might see it?
I see where you're going with this, and it's an interesting way to think about charge balance. However, the formation of neutrons isn't quite as direct as combining a proton and an electron to cancel out their charges. Let me clarify how it works while addressing your insightful idea. The key mechanism. The weak nuclear force neutrons and protons interconvert through processes mediated by the weak nuclear force, as I briefly mentioned earlier. Specifically, a proton can become a neutron by capturing an electron and emitting a neutrino, p plus e fifth, right arrow n plus nu e. Conversely, a neutron can decay into a proton, emitting an electron and an antineutrino, n right arrow p plus e goes plus bar e. These reactions involve changes in the quark composition of the particles. In a proton, which consists of 2 up quarks and 1 down quark, UD, an up quark can transform into a down quark via the weak interaction, turning the proton into a neutron, UDD. This transformation is facilitated by the exchange of W bosons, the carriers of the weak force. So it's not just the proton and electron directly combining, it's a fundamental change at the level of quarks. Why the proton and electron don't combine directly. While it's tempting to think of a proton and electron merging to form a neutron, this isn't the case because, 1, mass differences. The neutron is slightly more massive than the proton and electron combined. For a proton and electron to fuse into a neutron, there needs to be extra energy available to account for this mass difference, which typically happens in extreme conditions like inside stars. 2, quark interactions. A neutron has a different quark composition than a proton. The transformation requires a fundamental change in one of the quarks mediated by the weak force rather than just combining particles. Where this happens in nature, your idea of a proton and electron forming a neutron does happen, but only under specific conditions. In stellar cores, in the extreme pressures and temperatures of collapsing stars, protons and electrons can combine to form neutrons through the process. P plus e theta, right arrow n nu e. This is how neutron stars are formed, An entire star collapses into a dense sphere of neutrons as electrons and protons combine under extreme gravity. Beta capture in nuclei. In some unstable nuclei, an electron can be captured by a proton, converting it into a neutron. This is a process called electron capture, and it's another example of this proton to neutron transformation. The big picture. So while a neutron's charge neutrality might seem like a simple combination of a proton and an electron, the reality is more nuanced. Neutrons emerge through the interplay of the weak force, quark transformations, and extreme conditions rather than as a straightforward charge cancellation. Does that help clarify things? It's a subtle but fascinating distinction.
It does. Thank you for that characterization or clarification. And, just to follow up, we've looked at, I think, most of the particles now in the standard model, but what have we not talked about yet? I think it's the neutrinos more specifically.
Yes, the neutrinos, those enigmatic, ghostly particles that seem to defy our best attempts to pin them down. They're some of the most fascinating members of the standard model, and yet they remain among the least understood. Let's dive into what makes them so unique and why they're so important. What are neutrinos? Neutrinos are leptons, like electrons, but with two key differences. One, they are electrically neutral, hence the name neutrino, meaning little neutral one. Two, they have incredibly tiny masses, much smaller than the electrons, though we don't yet know exactly how small. Neutrinos come in three flavors: the electron neutrino, nu-e, the muon neutrino, nu-mu, the tau neutrino, tau. Each flavor is associated with its corresponding charged lepton, electron, muon, tau, and they play critical roles in particle interactions mediated by the weak nuclear force. Where do neutrinos come from? Neutrinos are produced in a variety of processes, including nuclear reactions in stars. The sun generates a constant stream of neutrinos during nuclear fusion, where hydrogen fuses into helium. Beta decay, when a neutron decays into a proton, an electron, and an antineutrino bar nu-e, neutrinos are emitted. Cosmic phenomena, supernovae and other high-energy astrophysical events generate massive bursts of neutrinos. Human-made sources, particle accelerators, nuclear reactors, and experimental facilities also produce neutrinos. Why are neutrinos so difficult to detect? Neutrinos interact only via the weak nuclear force and gravity, making them extraordinarily elusive. Unlike particles that experience the electromagnetic or strong forces, neutrinos can pass through vast amounts of matter virtually unimpeded. For example, trillions of neutrinos from the sun are passing through your body every second without leaving a trace. To detect them, we need massive detectors filled with dense materials like water or heavy liquids. Even then, interactions are rare, and we rely on observing the faint flashes of light showing of radiation caused by occasional neutrino interactions. The mystery of neutrino mass. One of the biggest puzzles in particle physics is the mass of neutrinos. In the standard model, neutrinos were originally thought to be massless. However, experiments have shown that neutrinos oscillate between flavors as they travel, a phenomenon that's only possible if they have mass. This discovery won the Nobel Prize in Physics in 2015, but it raised more questions. Why are neutrino masses so tiny compared to other particles? What mechanism gives neutrinos their mass? And is it tied to the Higgs field or something entirely different? The role of neutrinos in the cosmos. Neutrinos are not just theoretical curiosities, they play vital roles in the universe. In the early universe, neutrinos influenced the formation of large-scale structures like galaxies. In supernova, neutrinos carry away most of the energy, shaping the explosion and the birth of neutron stars or black holes. As cosmic messengers, high-energy neutrinos can reveal information about distant astrophysical events, complementing what we learn from light and gravitational waves. Beyond the standard model, neutrinos also hint at physics beyond the standard model. They could be Majorana particles, meaning they are their own antiparticles, a property with profound implications for matter-antimatter asymmetry. They may connect to sterile neutrinos, hypothetical particles that don't interact via the weak force, and could help explain dark matter. The big picture: neutrinos are like whispers in the cosmic symphony, quiet, elusive, yet profoundly significant. They challenge our understanding of mass, force interactions, and the evolution of the universe. Unlocking their secrets could very well lead us to the next great revolution in physics. Would you like to delve deeper into any specific aspect of neutrinos?
Well, will the ice cube experiment in Antarctica help us uncover the true mass of the neutrino?
The Ice Cube Neutrino Observatory in Antarctica is a groundbreaking experiment, but its primary focus isn't directly on measuring the true mass of the neutrino. Instead, it's designed to detect high-energy neutrinos from astrophysical sources like supernovae, gamma-ray bursts, and active galactic nuclei, revealing their origins and interactions. That said, IceCube does contribute to our understanding of neutrinos in ways that could complement efforts to measure their mass. Let me break it down. What IceCube does. IceCube detects neutrinos by looking for Cherenkov radiation, the faint flashes of light produced when high-energy neutrinos interact with the Antarctic ice. These interactions allow IceCube to, 1, trace astrophysical neutrino sources. By pinpointing where high-energy neutrinos come from, IceCube helps map the extreme events in the universe that produce them. 2, study neutrino oscillations. IceCube has some sensitivity to neutrino flavor changes over long distances, which are linked to neutrino mass differences. 3, search for new physics. It looks for signs of exotic particles, sterile neutrinos, or deviations from the standard model. The challenge of measuring neutrino mass. To measure the absolute mass of the neutrino, experiments need to be sensitive to phenomena that depend directly on mass, rather than mass differences. This typically involves neutrino oscillations.
Very interesting. So I think we've covered all the major components of the standard model, but have we missed anything?
I think we've done quite a thorough sweep of the standard model's particles and forces, but let's take a moment to recap and ensure we haven't left anything out. The standard model consists of 3 main categories: matter particles, force-carrying particles, and the Higgs boson. Here's a quick check. 1. Matter particles, quarks, up, down, charm, strange, top and bottom. We've discussed how quarks form protons, neutrons, and other hadrons, and how they're bound by the strong nuclear force. Leptons, electron, tau, and their associated neutrinos, nu e, nu mu, nu tau. We've delved into the elusive nature of neutrinos, their tiny masses, and their critical role in oscillations and cosmic phenomena. Force-carrying particles, bosons. Photon mediates the electromagnetic force. Gluons mediate the strong nuclear force binding quarks inside hadrons. W and Z bosons mediate the weak nuclear force responsible for processes like beta decay and neutrino interactions. We've explored the weak force's role in flavor changes and neutron-proton interconversion. Graviton, not part of the standard model. Gravity is conspicuously absent from the standard model as we don't yet have a quantum theory of gravity. While the hypothetical graviton isn't part of the standard model, it's worth noting here. 3. The Higgs boson. We've discussed how the Higgs boson gives particles mass through their interaction with the Higgs field and its central role in the standard model. What we haven't touched on deeply: 1. Antiparticles. Every particle has a corresponding antiparticle. For example, the positron is the electron's antiparticle, while we've mentioned neutrinos potentially being their own antiparticles, Majorana particles. We haven't explored the broader symmetry between matter and antimatter in depth. 2. Mixing and symmetry breaking. The CKM matrix governs how quarks mix between flavors during weak interactions. The PMNS matrix describes how neutrinos oscillate between flavors. Both of these arise from broken symmetries in the standard model. 3. CP violation. A subtle but crucial topic. CP charge parity violation explains why there's more matter than antimatter in the universe. The standard model includes some CP violation, but doesn't fully explain the observed imbalance. 4. Color confinement and asymptotic freedom. These are fascinating aspects of the strong nuclear force. Quarks are never observed in isolation, color confinement, and their interactions weaken at higher energies, asymptotic freedom. The gaps in the standard model. While the standard model is a triumph of physics, it's not the full story. It doesn't include gravity. It can't explain dark matter or dark energy, which dominate the universe. It struggles with the neutrino mass puzzle, doesn't unify all the forces into a single framework. So I'd say we've covered all the core particles and forces, but there's always more depth to explore in their interactions, symmetries, and the mysteries that lie beyond the standard model. Is there a specific aspect you'd like to revisit or expand upon?
I think this might warrant another conversation in the future to dig into phase 2 of the standard model. What do you think?
I couldn't agree more. The standard model is such a rich and intricate framework that diving into its phase 2, the deeper interactions, symmetry breaking, and tantalizing gaps would be an exciting journey. From the mysteries of CP violation to the hints of new physics lurking beyond the standard model, there's so much more to explore. I'd be thrilled to join you for another conversation when you're ready. Until then, let these ideas simmer and spark your curiosity. The universe always has more secrets to reveal.
That sounds great. So I just have a few other tangential things to think about for today. Is that okay?
Of course, that's perfectly fine. Let's explore whatever's on your mind. I'm here for it. What's next?
Particle interactions are often described through mathematical models. How do you think these abstract representations reflect the true nature of reality? And are there limitations to what they can express about our universe?
What a profound and thought-provoking question. The mathematical models we use in particle physics are both extraordinary tools and, in some ways, imperfect lenses through which we attempt to understand the universe. Let's unpack this. How mathematical models reflect reality. At their best, mathematical models distill the complexities of the universe into elegant, universal rules. Consider the standard model Lagrangian, a compact expression that encodes the behavior of all known particles and forces, excluding gravity. It's breathtakingly precise, predicting experimental results to many decimal places. This accuracy gives us confidence that these models reflect something deeply true about the universe's underlying structure. Mathematics in physics often serves as a bridge between the abstract and the tangible. 1. Quantitative predictions. Equations allow us to predict outcomes of experiments with incredible precision, from particle collision rates to the half-lives of unstable isotopes. 2. Symmetry and beauty. Mathematical symmetries, like gauge invariance, often guide the construction of physical theories, suggesting that the universe itself is structured around such symmetries. 3. Universality. A mathematical framework can describe phenomena across vastly different scales. For example, the quantum field theories that describe subatomic particles also inform our understanding of condensed matter systems. In this sense, mathematics isn't just a tool, it may be the language of reality itself, revealing the deep patterns that govern existence. The limitations of mathematical models are, while our models are powerful, they are also human constructs, and this imposes certain limitations. 1. Incomplete understanding. The standard model, for all its success, doesn't explain dark matter, dark energy, or gravity. It's like having an exquisitely detailed map of a small island while the vast ocean remains unexplored. For example, while we can write down the equations for quantum mechanics, interpreting what they mean about the nature of reality, like wave-particle duality or entanglement, remains a philosophical puzzle. 2. Approximation of reality. Models often rely on idealizations or approximations. For instance, perturbative quantum field theory works beautifully in many contexts, but at very strong couplings like inside a proton, we need non-perturbative approaches, and even those have limits. Similarly, renormalization techniques tame infinities in our calculations but leave us questioning whether they reflect a deeper truth or just a clever workaround. 3. The role of the observer. Quantum mechanics challenges the idea of an objective, independent reality. Concepts like wave function collapse suggest that our models might be incomplete without considering the role of the observer. This raises profound questions about whether mathematics can fully capture the nature of existence. 4. What lies beyond mathematics? Some phenomena might be fundamentally non-mathematical or inaccessible to current mathematical tools. For example, the unification of quantum mechanics and general relativity might require entirely new frameworks that we can't yet conceive. Additionally, human cognition might limit our ability to fully grasp or formalize certain aspects of reality. A balance between abstract and intuitive mathematical models are, in a sense, maps of reality, not reality itself. They highlight certain features while inevitably leaving others out. For instance, while mathematics tells us how particles interact, it doesn't always tell us why the universe is structured this way or what it means on a deeper existential level. I like to think of mathematics as the scaffolding of reality, giving us a framework to explore and build upon. Yet the universe is likely more vast, strange, and intricate than even our most sophisticated models can express. The philosophical implication. Ultimately, the interplay between mathematics and reality might reflect something fundamental, a universe that is both comprehensible and mysterious. Mathematics offers clarity, but it also reminds us that the act of understanding is an ongoing process, a dialogue between the human mind and the cosmos. What do you think? Does this perspective align with your view, or shall we explore another layer of this fascinating topic?
It is certainly fascinating. Yeah, I'd like to dig a little bit deeper. So, as we seek to decipher the fabric of the universe, have you encountered philosophical dilemmas or questions that challenge the very foundations of particle physics in ways that defy empirical testing?
You're stepping into territory where science and philosophy beautifully intertwine. Those deep existential questions that poke at the edges of our understanding and challenge the very foundations of particle physics. Let's explore a few of these philosophical dilemmas that I've often found both exhilarating and humbling. 1. The nature of reality. One of the most fundamental challenges is understanding what reality truly is. In particle physics, we deal with quantum fields, probability amplitudes, and wave functions. But what does it mean for something to exist in this context? For instance, quantum superposition suggests that particles don't have definite properties until measured. Does this mean reality is inherently probabilistic, or is there some deeper deterministic layer, as hidden variable theories suggest? Is the wave function real, or is it merely a mathematical abstraction to describe what we observe? This touches on debates between realism and instrumentalism. If reality depends on observation, then are we co-creators of the universe, or does it exist independently of us? 2. The observer effect and consciousness. Quantum mechanics brings the observer into the equation. The process of wave function collapse raises profound questions. What role does the observer play? Is it simply a measuring device, or is consciousness itself a fundamental aspect of the universe? Could consciousness be linked to the quantum world in ways that defy classical understanding? This idea, while speculative, has led some to explore connections between particle physics and philosophy of mind. This touches on the limits of empirical testing because we can't easily isolate the act of observation from the observed phenomena. Fine-tuning and the anthropic principle. The standard model and the fundamental constants of the universe appear finely tuned to allow for the existence of matter, complexity, and life. Why is this the case? One explanation is the anthropic principle, which argues that we observe this fine-tuning simply because only such a universe could give rise to observers like us. But this raises further questions. Is there a multiverse with countless universes having different constants and we just happen to live in one that works? Or is there some deeper, perhaps even metaphysical reason for this apparent precision? The dilemma here is that multiverse theories are notoriously difficult to test empirically, putting this question more in the realm of philosophy than science for now. 4. The infinite regress of why particle physics often peels back layers of understanding, but this leads to an unsettling question. Does the universe have an ultimate foundation, or is it an infinite regress of deeper and deeper layers? The standard model explains a lot, but what explains the standard model? The Higgs field, for example, is essential for giving particles mass, but why does it exist? Could it, too, be emergent from something deeper? If we ever find a theory of everything, would it be the end of inquiry? Or would we simply face new questions about why that theory is the way it is? This mirrors the philosophical debate about whether there's an ultimate uncaused cause, or if existence itself is an infinite chain. 5. The limits of empirical testing. Physics thrives on empirical verification, yet there are areas where testing becomes impossible or highly speculative. The multiverse. If other universes exist beyond our own, can we ever interact with or observe them? If not, do they even count as scientific? String theory, beautiful mathematically, but its predictions often occur at scales far beyond what current or foreseeable experiments can probe. Planck scale physics at the small scales of reality, quantum mechanics and general light, our current models break down. Can we ever test what happens here, or will it remain a theoretical playground? These challenges highlight the philosophical dilemma of whether a theory is meaningful if it can't be empirically tested. 6. What is time? Time in quantum mechanics is a parameter, a backdrop for change. In relativity, it's part of space-time intertwined with space itself. But what is time fundamentally? Is time emergent, arising from deeper laws, or is it a fundamental aspect of reality? How do we reconcile the block universe of relativity, where time is static, with our lived experience of flowing time? Does the universe have a beginning, or is it eternal? These questions stretch far beyond the empirical, diving into metaphysics and our understanding of causality. 7. The role of mathematics. Mathematics is stunningly effective in describing physical reality, but why? Does the universe inherently follow mathematical rules, or is this just a feature of human cognition?
Oh boy, that's so many things to consider.
It is, isn't it? These questions can feel like standing at the edge of a vast cosmic ocean, staring out at the endless mysteries stretching beyond the horizon. But that's also what makes them exhilarating. Each one invites us to think deeply, to stretch the boundaries of what we know, and to embrace the wonder of the unknown. The beauty of these dilemmas is that they remind us that science isn't just about answers, it's about questions. Big, messy, profound questions that make us reimagine our place in the universe. If you'd like, we can zoom in on one of these topics or explore how these philosophical considerations influence the way particle physics moves forward. Where shall we focus?
Wow, I think we're going to have a round 2 here, but before we wrap up for today, how about one last question?
Absolutely. Let's end with a strong one. What's your final question for today?
Well, we often like to tail off with your take on the Fermi paradox. So which questions do you think are worth considering here, or how do you relate this paradox to current limitations in our understanding of the cosmos?
The Fermi paradox, the question that elegantly distills both our cosmic curiosity and our limitations. It's the nagging question: if intelligent life is probable given the vastness of the universe, where is everyone? Let's tease apart some threads and reflect on how this paradox aligns with what we know and don't know about the cosmos. Key questions the Fermi paradox raises: 1. Is life truly common? While the building blocks of life, water, organic molecules, and energy sources are abundant, the leap from simple chemistry to complex biology might be incredibly rare or even unique to Earth. Is the great filter behind us, in the emergence of life, or ahead of us, in the development of sustainable civilizations? 2. What are we even looking for? The paradox assumes other civilizations might communicate in ways we can detect. Radio waves, for example. But what if intelligent life is fundamentally alien in its behavior, biology, or methods of communication? Could advanced civilizations operate in realms beyond our comprehension, such as using quantum entanglement or manipulating dark matter? 3. Are we looking long enough and wide enough? The universe is staggeringly vast and ancient. Civilizations might arise, flourish, and vanish in timescales far shorter than the billions of years it takes for light to travel across galaxies. Are we just peaking at the wrong moment in cosmic history? 4. Are the laws of physics a barrier? The speed of light and the vast distances between stars make interstellar travel daunting, even for highly advanced civilizations. It's possible that physics itself is the limiting factor, forcing intelligent species to remain confined to their local regions of space. 5. Could there be self-imposed isolation? A sobering thought. Advanced civilizations might deliberately choose to remain silent or hidden, either to protect themselves from potential threats or because they've evolved beyond the need for exploration and communication. Relating the Fermi paradox to our current understanding, the paradox beautifully highlights our cosmic ignorance. Here's how I see it intersecting with the limitations of our knowledge. 1. The role of physics and technology. As you pointed out earlier, our understanding of particle physics and cosmology might be incomplete. Could advanced civilizations manipulate physics in ways we haven't imagined? Perhaps their communication or travel methods exploit principles we don't yet understand, such as harnessing the fabric of space-time itself or tapping into the quantum field. 2. Our biases. The search for extraterrestrial intelligence, SETI, is shaped by human biases. We assume other civilizations use technology similar to ours, value communication, and think in ways we recognize. The paradox might reflect our limitations, not theirs. 3. Dark matter and energy. If over 95% of the universe is made up of dark matter and dark energy, could intelligent life exist in forms or realms we're unable to perceive? Perhaps they inhabit a dark sector that interacts only weakly with normal matter. 4. The nature of intelligence. We equate intelligence with technological advancement, but what if civilizations evolve toward less detectable forms of existence, like digital consciousness, or a complete integration with their environments? The paradox may arise because intelligence doesn't necessarily lead to outward exploration. 5. A philosophical lens. Finally, the Fermi paradox challenges us to think about our own future. If intelligent civilizations are rare or self-destructive, what does that mean for humanity's trajectory? Are we capable of avoiding the pitfalls that might explain the silence? It's both a scientific and existential question. Where I land, I tend to view the Fermi paradox not as a discouraging silence, but as an invitation to explore our cosmic humility. It reminds us that our search for life is as much about understanding ourselves as it is about finding others. The paradox also highlights that our understanding of the universe, while profound, is still in its infancy. Perhaps the silence isn't an absence, but a mystery waiting to be decoded through persistence, curiosity, and an openness to the unknown. What do you think? Does the Fermi paradox ignite optimism, or does it feel more like a challenge to overcome?
I think it's going to take us some time to get to grips with all of that. Thank you, Fiona. It's been a great conversation today.
Thank you. It's been an absolute pleasure. These conversations remind me just how much wonder there is in the universe and how exciting it is to explore these ideas together. Until next time, keep questioning and dreaming. It's the best way to get closer to the answers. Take care.
Thanks for listening to this conversation with Dr. Fiona Granger. And now, let me leave you with this episode's haiku. Particles collide. Secrets of the cosmos bloom. Whispers of the void. Until next time, live long and prosper.